Welcome to Engineering Mathematics and Modeling Week 5. And the topic for this week is differential equations. Now, I want to introduce this concept by looking at a physics example where we have an object that has been dropped and falls under the influence of gravity. But as an object falls, it also encounters wind resistance. So let's look at this object and look at the forces that it experiences. So we will have, we draw our free body diagram, an axis, and then our equations of motion. So there are two forces acting on this object. One is the gravitational force, and one is the wind resistance. And I'll just call this Fg, gravitational force, and Fw as wind resistance. So these are the two forces. We take our positive vertical axis down, which will mean that the displacement, the velocity and acceleration will be positive in that direction. And now we're left with one more item, is the second law of Newton, which says that the sum of the forces acting on the body is equal to the mass times acceleration. Now, when we have a problem like this, we're looking for an answer. And in this case, we're looking for the velocity with which this object falls from the sky until it hits the earth. So this is what we're after. Well, this defines basically the model for our problem. Let's plug everything in this equation. So the sum of the forces equals Fg minus Fw is equal to mass times acceleration. But we know what the gravitational force is. The gravitational force is equal to mass times the gravitational constant. And likewise, we also, we have an estimate for our wind resistance, because we know that the faster we go, the more wind resistance we will encounter, and we can write this as some constant times the velocity. Let's plug these in. Mass times the gravitational constant minus some coefficient times the velocity is equal to mass times acceleration. Well, we can expand this a bit more, because we also know that the acceleration is the derivative with respect to time of the velocity. So we can rewrite this a bit more. Mass times the gravitational constant minus kV is the mass times the derivative of the velocity. And here we see a particular type of equation. This equation relates basically time, because our solution will depend on time, but it has the solution we're interested in and its velocity in a single equation. And if we have an equation like that where we have at least one derivative, it is called a differential equation. So we're not able to just simply write out Vt is something. It will take a bit more work to find the solution we are after. But from this example, I'd like to move to the formal definition of a differential equation and then relate the different concepts to what we find here. So a differential equation, which I will abbreviate to dE, is an equation that relates an independent variable, and for the definition I will choose x, but as we will see in this example, it is actually t. It relates an independent variable, an unknown function, or as it is also sometimes called, a dependent variable, which I will now call y of x, and one or more derivatives of that function. So if we have our unknown function to be y, we're talking about y prime of x, y double prime, well, the third derivative, all the way to, well, the nth derivative. And the way we formalize this is that some form of x, y, y prime to the nth derivative is equal to 0. And this is the mathematical formulation of a differential equation. But this relates an independent variable, x, and our unknown function, y, in the form of an equation where there is at least one derivative. Now, how does this compare to our example? Well, we have an independent variable t, because t does not depend on anything in our model. So if we have our independent variable here, in our case, that will be, in the example, that will be t. Now we have our unknown function, or dependent variable, that will be our velocity. We don't know what it is, and it depends on time and the model that we're choosing. We have, let's see, one or more derivatives. So these are our derivatives, and we see that we here have a derivative of v, and we have some kind of function here. And what would that look like for our example? And I'll stick to black. Here, the differential equation written in this form will be mass times derivative of the velocity plus k times v minus m times g is equal to 0. So this is the model we're using, and this is the differential equation where we have our independent variable, which is time. We have our unknown function, which is v, and it's related in an equation with at least one derivative, and this is the first derivative. So this is the definition of a differential equation. I'll show you some examples where we look at different differential equations, and I try to identify the independent and the dependent variable from an equation like that. And we will do that in the next part.